This lecture, we are going to build on some of what's talked about in the microwave engineering course, and rather than go real heavy into transmission line theory, we're not going to do that. We're just going to talk briefly about transmission lines, and then talk about embedding those transmission lines in anisotropic media. And the conclusions from that, in fact, can be generalized to a number of devices. In fact, we're just using transmission lines to illustrate what would happen by embedding a device in an anisotropic media. So we'll briefly discuss transmission lines, talk about some theory about transmission lines embedded in anisotropic media. That will tell us if our modeling results make any sense. And the bulk of this presentation will talk about how to use finite difference analysis to model transmission lines embedded in anisotropic media. And in fact, we can do some really neat things by doing this. At the very end, I want to generalize this method and show you really what it is you will have developed in this code and what you can do with it. We're using it here to model transmission lines, but in fact, it can do a whole lot more. So transmission lines are waveguides, but not all waveguides are transmission lines. Transmission lines have at least two conductors. So this means if it's carrying electromagnetic power, in fact, if it has more than two conductors, it goes all the way down to DC because we have two wires. One can be positive, one can be negative. Current going in, current coming out. Whereas a waveguide can be, for example, just a metal pipe. That will have a cutoff and does not go down to DC. So it has a cutoff frequency. Transmission lines can go all the way down to DC. So some of the more common ones I have illustrated here. Perhaps the most famous and most common is this microstrip transmission line, or that's just an ordinary circuit trace. And there's a ground plane, there's a slab of dielectric, and then your signal trace. And of course the electromagnetic field establishes itself mostly between the two plates, but it surrounds a little bit. Then we have a coaxial cable. That's very common, or used to be common, for porting your video into your television. Strip line can be thought of more as a buried microstrip. If we via down into a printed circuit board, the embedded microstrip, if you will, is really called a strip line because now it probably has a ground plane above and below it. Slot line, where there's just two metal plates and the field establishes itself at the gap. Now there's many more transmission lines. These are just some common ones, and the example that we'll build in this lecture is the microstrip. One place to start, we can analyze this microstrip as a capacitor. In fact, we'll do this in our numerical method, but folks can do this analytically, and they've derived, this group that had the reference at the bottom, derived an analytical equation for calculating the characteristic impedance of a microstrip transmission line. The reason this is useful is we can use that to test to see if the program that we're going to write here works. To simplify things, we are going to make an electrostatic approximation. Now, to be complete and accurate, a transmission line is a waveguide and should be modeled as such. It's just that the fundamental mode is very near TEM, or transverse electromagnetic, because it's so small relative to the wave. Because it's very nearly TEM, in fact, the electrostatic approximation really does predict a purely TEM mode. And we can simplify this way down and make the numerics a lot easier and the analysis a lot easier. But we're not going to be able to calculate multiple modes. If at very high frequencies, all of these transmission lines become multimoded. We're not going to be able to calculate that with our electrostatic approximation. We'll only be able to calculate the TEM mode. Well, what do we buy for that? A lot of speed, efficiency, simplicity, and for the most part, transmission lines are really only ever used with that TEM mode. It's rare to find them used with other modes, although it does happen. So, in the electrostatic approximation, we start with Maxwell's equations, and we set all the frequency terms or time derivatives to 0, and Maxwell's equations reduce to this. And one of the things we see is that the electric and magnetic fields actually decouple. And in fact, we would need to fully analyze the device, we need to solve these separately now. We need to solve the electrostatics problem and then the magnetostatics problem. When we analyzed waves, we used the wave equation. When we are analyzing an electrostatics problem, we use what's called Laplace's equation. And we want our model to be able to handle any kind of dielectric distribution outside of the transmission line, so it can be very inhomogeneous. So we need to derive what's called the inhomogeneous Laplace's equation. So we start with the divergence equation. We set the charge to 0, no free charges. We have our constitutive relation, D equals epsilon E. And we substitute that in, and now we have sort of a different divergence equation now in terms of the electric field E instead of D. But we know that the electric field is related to the scalar potential through the gradient. Well, now we can substitute the electric field into equation 2, and what we have is one big ugly differential equation. However, this is no longer a vector equation. It's a scalar equation in terms of the scalar potential V. And this is what we're going to solve. It's going to look a little bit different. We're also going to let the permittivity become anisotropic. But we'll solve this numerically and put that in matrix form. So let's assume we've solved it. We've calculated the scalar potential. Once we know the scalar potential, we can take the gradient, calculate the gradient, get the electric field E. Then we can go back to the constitutive relation and get the field D. Well, if we know D and E, in fact, we can calculate the total energy stored in that device. And it's an electrostatic model, so it's a capacitor. So this is the energy stored in a capacitor. We also know from circuit theory that the energy stored in a capacitor is related to the voltage across the capacitor and the capacitance through this equation. Well, we can plug in this big ugly expression for the energy down here, solve for capacitance, and now we have a way, given the scalar potential, that we can calculate the capacitance of that structure. So the missing step right now is, well, how do you solve Laplace's equation to calculate the potential? Once we have that, the analysis is pretty much done. We just calculate E and D from that, and then we can calculate capacitance. We also want the distributed inductance. If we had permeability or some kind of magnetic response around the transmission line, we really would have to go back to Maxwell's equations and solve those. If the magnetic response around the transmission line is at least homogeneous, it turns out it becomes a lot simpler because the velocity of the electric field and the voltage on the line is roughly the same, well, is the same. So the velocity in terms of the voltage on the line related to the transmission line parameters is 1 over the square root of L times C, where L and C are the distributed inductance and capacitance of the line. Well, if this were a wave in a medium, then the velocity is 1 over the square root of mu times epsilon. Well, we can solve this for LC, and that now equals mu times epsilon over C naught squared. So we have an equation, a simple equation, relating transmission line parameters to sort of effective material properties. And now we can solve this for L, and in fact now we have a way of calculating the distributed inductance, really having done an electrostatic model calculating distributed capacitance. Well, the best thing to do is to calculate the distributed inductance is to remove all of the dielectric from the transmission line and model the transmission line embedded in purely air. When we do that, we'll take this air transmission line, calculate the capacitance from it. We'll call that the capacitance of the homogeneous case, C sub H. And from that, we get the distributed inductance. Then we'll put those dielectrics back in, calculate the distributed capacitance again, and that will be the true distributed capacitance. So we really have a two-step model. Once we have the distributed inductance and the distributed capacitance, we can real easily calculate the characteristic impedance of the line. That's just square root of L over C. We can also calculate the velocity of the signal on the line. It's 1 over square root of LC. Once we know the velocity, then we can calculate an effective refractive index. That's simply the speed of light divided by the speed that we just calculated up here, or the speed of light times the square root of LC. And once we know the impedance and the effective refractive index, now we have everything that we need to use this in network theory. And if you've had a microwave engineering class, you'll recall that network theory is simply a modified version of circuit theory that takes into account the wave nature of signals on the lines. So for example, if you have a microwave signal traveling down a transmission line, the voltage is not constant along that line because it's a wave. Well, with traditional circuit theory, voltage is constant along a conductor. So we need to modify our circuit theory. That is called network analysis, and the impedance and effective refractive index are the two things you'll need about a transmission line to do network analysis with it. So as we mentioned before, we really have a two-step model now for modeling transmission lines. The first thing we'll do is remove any kind of dielectric. So we'll have a transmission line sitting in air. Even though we've got some kind of crazy coax that has two different dielectrics in the middle, we will remove that, replace everything around those metals with air. We will calculate the distributed capacitance using an electrostatic model. From the distributed capacitance for this air case, we'll get the true distributed inductance. Then we'll put all the dielectrics back in, solve the electrostatics problem, and get a distributed capacitance. Now we have the distributed inductance and capacitance from the line. So we really will model this transmission line twice. Once with the dielectric removed being all air, and the second time with all the dielectric being on the inside. So that's how we get L and C. Okay, so really here's the full picture of what we'll do. The first step of this process is the air coax, or air transmission line. So we build that on our grids. Then we construct and solve our matrix equation, and we'll talk more about this later. But once we solve this and we have the scalar potential, then we can calculate the distributed capacitance of that. Remember, this is the air case, so it's not the true distributed capacitance of our line. But then we can calculate real quickly the distributed inductance from that. And this is the true distributed inductance of the transmission line. Then we do another pass through this. We put the dielectrics back in. We do the same thing all over again. And we calculate our distributed capacitance. Then we can calculate our transmission line parameters. Characteristic impedance and effective refractive index are the two most fundamental ones. So now we will generalize this, and let's look at what happens when we embed our transmission line inside of an anisotropic material. So I'm looking at these four figures, and I'm in the upper left one right now. What we're looking at is a microstrip transmission line. So we see the signal trace, and down here would be the ground plane. And I'm drawing the iso contours of the electric field around that line. So this is for a standard microstrip. I'm drawing a lot of them. The field's pretty darn weak out here, but I'm drawing them anyway. So the first thing we'll do then, we'll take it from this isotropic material and put it in something that's anisotropic. But this is only a contrast of 2 and 10. But what we see immediately is that the field gets narrower and it grows taller. And it's actually starting to push itself in the direction of the highest dielectric constant. It's incorrect to say that it's propagating that direction because this is the near field around a device. It's not going anywhere. It's stuck to the device. So I like to use words like the field tends to develop in the direction with the highest dielectric constant. Well, let's go higher anisotropy, 2 and 30. Well, the field gets even narrower and even taller, and as we go up, narrower and even taller. So conclusions here, the big ones are the field tends to develop in the direction with the highest constitutive value, the highest permittivity in this case, and the greater the anisotropy, the more it tends to do that. Now let's look at the effect of of spatially varying the orientation of that field? Well, we start off in the upper left with our normal isotropic case, nothing interesting happening there. Then we stick it in something that's anisotropic with the highest dielectric constant being vertical, and the field follows that. Now if we take that and we tilt the tensor, rotate the tensor to the left, now what we see is the field is still following the anisotropy, it's just that the anisotropy is rotated. So it's following that dominant direction still. Well, what happens then if we spatially vary the orientation of the anisotropy? Well, it follows the highest dielectric constant. So suddenly, the near field around our transmission line becomes a lot like clay, and we can spatially vary the orientation of the anisotropy and sculpt what that looks like. Now there are some restrictions. Sometimes we need pretty high anisotropy, and we need some way to spatially vary it and rotate the tensor associated with the anisotropy. So here's what we did with this. We took a microstrip transmission line, and I'm looking at the upper left. This is an ordinary microstrip, and we're looking at the field around it. This came out of ANSYS HFSS. Then we put a metal ball up next to the line, and what happens is that near field gets perturbed. Notice these near fields look different, and because it's being attracted to the ball, and that's causing the properties of the line to change. Well, now we embed it in something that's anisotropic, where the anisotropy is tilting to the right, and we can see that the near field is tending to follow that direction of highest anisotropy. Then when we put the ball down, it turns out the near field is a lot less perturbed. And in fact, if we went to really strong anisotropy, this would be even a more extreme example. So the reason that the ball is not perturbing that near field nearly as much as it did before is because we've pulled the near field away from it. We've sculpted the near field around the transmission line to essentially isolate it from that metal ball. So here's our experiment. We took a microstrip transmission line, we hooked it up to our vector network analyzer, and what a vector network analyzer does, sometimes just called a VNA, is it pumps out a signal, and it looks at what gets reflected and what gets transmitted. And so we get transmission and reflection measured by our VNA. So we hooked up a regular transmission line, so we get near 100% transmission at first, and then we put a metal ball up next to that line, and then pull it away, put the metal ball up next to the line, pull it away, and what we see is the reflection and transmission jumps around. And the blue line over to the left is the change in the S11, or the reflection parameter, as we take the ball and put it up against the line and pull it away. So we see almost 7 dB jumps. The next thing we did is we took in this case it was a metamaterial, a spatially variant anisotropic metamaterial, and you'll see this dark spot right in the middle. That's a hole that we could drop the metal ball down. And what this does is sculpt the anisotropy around the line, and it essentially pulls the field in this upper right direction, pulls it away from where this ball would be so that it doesn't experience the ball. Well, when we put this in place and we drop the ball, and we drop the ball, bring it out, drop the ball, this red line is the change in the reflection, or the S11, when we do that, and we can barely measure any swing in the S11 parameter. So what has happened is this SVAM has essentially, or SVAM, spatially variant anisotropic metamaterial. Using anisotropy, we have essentially isolated that microstrip transmission line from a metal ball. Well, one of the cool things that we're doing now in a 3D printed system, where we have devices scattered in 3 dimensions, and it really becomes an electromagnetic mess, we're looking at this mechanism as a way of isolating components by sculpting all the near fields so that the devices don't interfere. And there's a bunch of other cool things we can do with this, but this was our first experimental demonstration using this concept. Okay, so now we want to learn how to model these devices. So this will be in 2 steps, the formulation and then the implementation. First, we need to talk about a grid. We really have 2 unknown functions here. Well, 3. We have the potential V, we have the electric field X, and the electric field D. But the D and E fields, from what we remember last semester, they really exist at the same points So we just need to look at where the electric field E's are and where the potentials are. And we distribute them on a grid this way. We're staggering them because we want to use central finite differences, so we stagger the grid. But we're going to place the potentials at the origins of the cells, and then the electric fields along the axes offset by a half cell. And that way, when we're taking derivatives of the electric fields, we end up right in the middle with a central finite difference where the potential is. And when we take derivatives of the potentials, we're using central finite differences, we end up right in the middle where the electric fields are. All the same reasons we adopted a Yee grid last semester. So this is our grid. The potentials and the electric fields are staggered, and we will write our finite differences consistent with this. We have the same three governing equations. We have the divergence equation, the constitutive relation, and then we have the electric field related to scalar potential. So I can expand these into vectors and matrices just like this. Now, this is clearly the next step that we're going to do is do our finite difference approximations. First, what we want to do is reduce our problem from 3 dimensions down to 2 dimensions and see what happens. Well, we know in a transmission line, nothing changes in that z direction. And this is an electrostatics model, so there's not even any phase accumulation in that z direction. So anytime there's a z derivative, we set it to 0. So what we do is we have our 3 governing equations, and anytime I see a z derivative, I set it to 0. Well, if we look at this, that means that it's not taking the derivative of z. And the only way really to reconcile this is if the z component is 0. And in fact, this is consistent with the electrostatic finding the TEM solution, where there is no z component. So if there is no z component, we'll just write this divergence equation with only the x and y components. Now we go down and we look at the constitutive relation. We already know that dz is 0. Well, this implies also that ez is 0. Again, consistent with this being a TEM solution. There can't be any z components. Well, if there are no z components for E or D, then we can write this tensor equation just with these 4 tensor elements. EXX, or epsilon XX, epsilon XY, epsilon YX, and epsilon YY. And in fact, all the other tensor elements, these 3 in this column and these 3 in this row, the transmission line is independent of what those are. They could be anything, and the transmission line won't feel that. Okay, so how is the electric field related to scalar potential? The z component is 0. And so, well, it turns out, and also the z derivative is 0. Well, we can reduce this to 2 dimensions too, and just relate the x and y components to the scalar potential. So we now have 3 simplified equations for our transmission line analysis. We're really just looking at the cross-section of the transmission line. So we're done with our governing equations. Now we write this in matrix form. And based on what we did last semester, we don't actually have to touch explicitly the finite differences. And we can take our analytical derivatives, and these are our derivative operators for taking derivatives of the electric fields. Our D fields are column vectors, so they have these bold lowercase d's. Our constitutive relation becomes this matrix equation. We'll talk a little about that in a second. And then electric field rated to scalar potential through this equation. And now we have derivative operators operating on the scalar potential V. Now back up to the constitutive relation. This demands more attention because in fact this is not correct as written and we need to modify it. So here's the equation where there was an issue. This matrix equation is representing 2 separate equations. And now what we want to do is write this on our grid with finite difference approximations. There's no differences, so we don't see any finite differences, but we definitely see the grid coordinates I and j. So are these equations correct? Well, remember the staggered grid. So in fact, this EY component does not exist at the same point as EX and DX. Well, that's a problem for this equation. Remember our golden rule for finite difference equations. Every term in that equation has to exist at the same position in space, and it's not satisfied there, so that's a problem. And likewise, the second equation, this EX field exists at a physically different point than dy and EY. So that's a problem. We need to fix these. And in fact, what we need to do is take these terms and average them and essentially interpolate this term so that it is at the same point as the other two terms in the equation. And we talked about this last semester in Computational Electromagnetics, and we introduced these interpolation matrices into our finite difference equations, which did the averaging for us. So we're going to use that again. So here's how we do that. The matrix form of these two equations is down here. We're introducing two interpolation matrices here and two interpolation matrices here. Let's look at what's happening. So for example, we have an equation for dx. So let's just pick this point, just so we're in the middle of the grid somewhere. What we want to do is interpolate EY to exist at the same point as EX. Well, what I need to do is average this EY with the EY in the next cell over in the X direction. We need to average these. So that's what this interpolation matrix does. It averages in the X direction and it reaches forward. That's what the positive superscript means. Okay, so we've just averaged these two, and now we have an electric field that's essentially right here. Well, what we need to do is average this with another electric field that hopefully we just averaged up here. So we need to average now in the Y direction, but we need to reach to the previous cell this time when we average in the Y direction. So we average in the Y direction, and we reach to the previous cell, thus the minus superscript. And we won't talk through it, but in fact, this term needs to be interpolated in the X direction, reaching to the previous cell, and in the Y direction, reaching to the next cell. So we insert these interpolation matrices, and now we have fixed finite difference equations. This will work because all of the terms exist at the same position in space. Okay, so here we are. We have our three governing equations on the left, and those three governing equations in matrix form on the right. Now we're ready to solve these. So the first thing we'll do is derive the matrix form of the inhomogeneous Laplace's equation. Remember, we also need the homogeneous Laplace's equation. So here we have our three equations in matrix form, equation 1, 2, and 3. The first thing we'll do is we will substitute equation 2 into equation 1 to eliminate the D fields. And here's where we end up when we do that. Second thing we do is we substitute equation 3 into this new expression to eliminate the E fields. Now we have a single matrix equation with just one unknown instead of two. So it's actually a simpler equation. It's scalar, it's not vector. And we can multiply both sides by -1 to get rid of the negative sign. And here's actually the final equation. That is the matrix form of the inhomogeneous Laplace's equation. And here we have derivative operators that operate on the electric fields. And here we have derivative operators operating on the scalar potential. So just like E and H when we did the E grid stuff last semester, in this case we have E and V, which are staggered. So we still have a E grid type of thing happening here. Now in the homogeneous case, what was written like this for the anisotropic case really just becomes an identity matrix. Well, if we stick the identity matrix in the inhomogeneous Laplace's equation, we see that we can just drop this matrix entirely and just write it as really the inner product of those two gradient operators, if you will. So this is now the matrix form of the homogeneous Laplace's equation. Well, we can't solve this yet. We have a matrix equation really in the form of LV equals 0. L being all those terms collected into the matrix form of Laplace's equation, V being a column vector of the unknown potentials, but then all of that equals 0. That's not solvable. If we backward divide by L, we just get a trivial solution for V. So, well, why is that? That's because we have not applied a voltage. Once we apply a voltage to our capacitor, then we can calculate the potential between the plates. So it makes sense that this doesn't really have a solution, because how would it know what the potential is if we haven't told it what voltage is applied? So the next step is to tell this model what voltage is at what point on our grid, and enforce that in some fancy, easy way. And then we can calculate the potential everywhere else. So how do we do this? In fact, in this case, it's not as simple as just coming up with a column vector on the right. We'll call that B. We also have to modify L. So what we want to do, really, suppose there's a point on the grid that is a metal. So if it's a metal, then we have to force it to some potential that we need to know ahead of time. So let's say it's at point M on the grid. So where there's metal, we want to set it to some applied voltage. Well, so we want this row through our matrix equation to represent this simple equation to force this point on the grid to some applied voltage. So what I like to do is just make the entire row in this matrix L zeros. We'll stick a 1 in whichever position along here is in the center diagonal. We don't touch this column vector, these are unknowns. But over here in B, at this position, we put in the applied voltage. So if we read off what equation this row represents, it's exactly this equation. So we've erased what was there and replaced it with an equation that simply said the potential at this point is that. And so we modify L, we modify the rows in L and the row in B wherever there's a metal in our grid and we're forcing it to some known potential. So here's a fancy way of doing this that actually works a lot quicker than setting up a for loop, in MATLAB anyway. We'll come up with what we call a force matrix. This is similar to the Q matrix that we did when we were doing sources in finite difference frequency domain. So this is a matrix, and along the diagonal, the center diagonal, we place 1s in every position that is a metal that we are going to force to some potential. Then we will construct a column vector. And in that column vector, we will list all of the forced potentials. If there's a position that's not a forced potential, it actually doesn't matter what number we put there. It will get ignored. So we'll just keep it at 0. So anywhere there's a metal, we will stick what voltage we are connecting that metal to in that column vector V sub F. Okay, so what's a fancy linear algebra way to do this? Well, the first thing we want to do is replace all of the rows in L where there's forced potentials, replace all of those rows with all zeros. Well, a way to do that is to take that original matrix L and just multiply it by the identity matrix minus F. We'll get essentially the same L back, except all of the rows that we will force to a potential will be all 0. The next thing we want to do is place a 1 along the diagonal position where there are force potentials. So all we have to do then is add that force matrix to what we just calculated in the previous step. That's our modified L. We also need to construct B. That's simply a column vector of all the force potentials. So here's our force potentials. If we multiply it by F, that will essentially zero out all the ones that are not forced, that are in dielectric that we need to figure out. So just F times this column vector gives us our B. And now we're ready to solve for the scalar potential. So that's the formulation. Now what we'll do is we'll step through this step by step. How would your program work? Well, step 1, before we even get to the program, we need to define what on earth it is we're modeling. Well, it's a microstrip. It has some width W, the substrate has some thickness H, the superstrate, the area above the transmission line, has some dielectric constant, and the substrate has some dielectric constant. If you really want to have a fancy model, we can also input the thickness of the microstrip, but we'll just assume that that's one cell and really thin. So we're also formulated something that can handle anisotropy. So in fact, we need to define the tensors in the superstrate and substrate. We'll just let the superstrate be air and the dielectric substrate just be 9s along the diagonal. So we actually have an isotropic case. We'll let the width of the line be 4 millimeters and the height, the thickness of the dielectric be 3 millimeters. So we've defined our line. We'll have a dashboard in our program where we hard code all these numbers. And then after that, it will just all be calculations. So we have all the parameters we need. The first thing we'll do is we'll calculate a grid and then build our microstrip or transmission line on it. So what we need to think about is the strategy in doing that. So it'd be pretty obvious how to put the substrate on here in the center of the microstrip and all that, but we need regions, and I'll call them spacer regions, between the microstrip and the edge of the cell. We will be using Dirichlet boundary conditions in our derivatives. That means it will force the scalar potential on the outside to be zero. Well, so if we move the boundaries up too close to that transmission line, physically it wouldn't really be zero there. So we need the boundary to be far enough away that, yeah, that scalar potential really is zero by the time it gets there. And how do we determine the size of the spacer region? We look for a convergence. We keep making it bigger until the answer doesn't change much anymore. In our model, we will be building 6 different arrays. 2 of them will be on a 1x grid, and 4 of them will be on a 2x grid. Recall that, the 1x, 2x grid thing from the Computational Electromagnetics class. Same concept, because we're using this staggered nature, so it's easiest to go to a 2x grid when we're building our dielectrics, I think. On the 1x grid, we have 2 arrays, and in fact we could have more, but each array is describing a separate conductor. We have a signal, so this will be all zeros except ones right where the microstrip trace is. Then we have grounds, anywhere we want grounds. Well, it's obvious why we want the ground on the bottom, because our microstrip is sitting on top of a big ground plane. But I like also to put grounds all the way around. And when we use the Dirichlet boundary conditions, and because we're using these staggered derivatives, in fact, on one side it forces the potential to zero, on the other side it forces the electric field to zero. And we get a little bit of asymmetry just in our boundary conditions there. So the fields around the transmission line tend to look like they're getting sucked towards one side or the other just due to that asymmetry. If those boundaries are far enough away, it's really not that big of a deal. I just like to put this in so things look symmetric and they look prettier, but it's actually not needed. And it does not improve the accuracy, it's just the answer looks a little bit prettier. So we could leave all zeros along the left, top, and right sides here, but we definitely need ones along the bottom as our ground plane. Then on the 2x grid, we really have just these 4 tensor elements left, and we build 4 separate arrays. Now this is isotropic, so the x, y, and yx cases are really all zeros. So these will be completely zeroed out. The ER2XX and ER2YY look the same, although we realize on the 2x grid thing they may differ by 1 cell around the boundary, just depending where things lie. But for the most part, everything looks the same. But the off-diagonal tensor elements will all be zeros. So when we have these 6 arrays, we can say that we've built the device and now we're ready to start doing the linear algebra stuff to calculate the potential around the transmission line. So first thing I like to do is calculate our derivative operators. Well, no need to reprogram a derivative operator constructor. We can use the YDER that we did last semester. And we'll use it this way. We have the size of the grid, the resolution, the boundary conditions, and we call the exact same function. Now before, when we used it for the Y grid, when we had E and H fields, the first 2 outputs were the derivatives for the electric fields, and the second 2 were the derivative for the magnetic fields. Notice the order here. Now we have the first 2 derivatives being for the scalar potential, and the second 2 being for the electric field. So notice that difference. We also need our interpolation matrices. And recall from our last lecture, or from when we talked about this in computational electromagnetics, those interpolation matrices are very, very close looking to the derivative operators. And in fact, when we're using Dirichlet boundary conditions, we can calculate them directly from the derivative operators. So for the details of that, I would refer you back to the lecture in computational electromagnetics. But these are the equations we'll be using to build these. We calculate the interpolation of Rx in the positive direction. We take the absolute value of dVx. Our finite difference is one term minus another over spacing. This makes it one term plus another divided by spacing. Well, we multiply by the spacing, so now we just have one term plus another, and divide by 2, and that's interpolating at the middle point. And then we do the same thing, ry in the minus direction, and we use dEy for that. And then we calculate sort of a composite interpolation matrix that'll actually be interpolating over 4 surrounding points, and we put these together. And we will use this when we build the dielectric tensor. So from EDER, we get our derivative operators, and we also get our interpolation matrices. So we don't have to write a separate function to do that. Now, if we were using periodic boundary conditions or something else fancy from EDER, we would probably need a separate function to do our interpolation matrices. But since we're using Dirichlet, we can do it like this. Well, now we want to diagonalize our tensors. So the first thing we do, we have our tensors on a 2x grid. We need to parse those down to a 1x grid, but we'll come away with 4 arrays on a 1x grid. Then we diagonalize those and make sure that they're sparse matrices. So now we have 4 matrices that are diagonal. And then we assemble these together and we put in this composite interpolation matrix, if you will. And now our ER tensor looks like this. The center diagonal just has diagonal elements, but notice the off diagonals have 2 lines. That's because it's doing an interpolation there. In fact, there's probably more than 2 lines. I drew it like that more as a cartoon than anything. So now we have our diagonal tensor for the dielectric. We need to build 2 different L's. This is the matrix form of the Laplace's equation. We need one for the inhomogeneous case and one for the homogeneous case. So for the homogeneous case, I like to put a little h after the L. So we build the inhomogeneous Laplace's equation. Notice we have our derivatives for e's, derivatives for v's, and here's this tensor. And for the homogeneous case, it's the same thing. There's just no tensor in here. And if we were to plot what L looks like, it looks something like this. The next thing is to force the known potentials. We have really 2 conductors here. We have our ground that we will force to 0, and we have our microstrip. We're free to force that to any voltage. 1 is convenient. So we need our force matrix. So the first thing I do, sort of like when we calculated the Q matrix last semester, is I'll take the signal array and the ground array and I'll OR that together. So what we have is an array of all zeros except there's ones in the positions where there's conductors. Then we diagonalize that. So this is a diagonal matrix and it has ones going down the diagonal in the positions corresponding to where there's metals. Then we need a column vector containing what we're forcing everything to. Well, everywhere there's a signal conductor, we'll force to 1, and everywhere there's a ground, we'll force to 0. Now, if we actually don't need to include this term, it just makes a little bit of sense to put it there. But if we didn't include that term, the positions with grounds would be 0 by default anyway. But I like to write that just so I can see what I'm doing. And maybe if for some reason I'd want to put the ground at some other potential, and I can do that now. So now I have the 2 matrices I need to modify the L's and create our B matrix so that we can solve it. So here's the original L matrix, and we modify it to get a revised L matrix. And what we've done here, remember, we replaced all the rows where there's metals with all zeros, and we put ones in the diagonal position. We do that for both the inhomogeneous and the homogeneous L. Then we construct the B, and this is a column vector that has all zeros, except in the positions where there's metals, we have the applied voltage. So if we were to plot B, we would get something like this. Reshape it back to a 2D grid, we'd see we'd have ones here, zeros for all these ground positions, and also zeros for in here because those are sort of the don't care positions. They're the ones that we're calculating. We don't know them yet. Well, here's the big step, the simplest in code, but the computationally most intensive. Here's where we calculate the scalar potential using backward division. So we have the inhomogeneous scalar potential and the homogeneous scalar potential. Well, once we have the scalar potential, calculating the E and D fields is quite easy. So to calculate the E fields, it's this gradient vector times the scalar potential. Don't forget the negative sign here. And we do the same thing for the homogeneous case. Then to calculate the D fields, we go back and we use the constitutive relation. However, for the homogeneous case, the D and the E fields are the same thing because our dielectric tensor is the identity matrix. We made it all in air, so the dielectric constant's all just ones and is isotropic. So the big step here was calculating the scalar potential. After that, it was real quick and easy to calculate E and D. Well, once we have E and D, now we can calculate the capacitance using our original equation. So to do this double integral, in fact, we have D and E in column vectors. So we multiply those together, but we transpose the D field. And so this is called an inner product. But what it's doing is it's multiplying all these and adding them all up. Then we multiply by the dx and dy. That's essentially our dA. We applied 1 volt, so we're not dividing by that. But do notice that we're multiplying by epsilon naught here. That's the free space permittivity. Technically, that should have been when we put in when we did our constitutive relations, but I like to leave D and E the same order of magnitude. So I just cheated a little bit and pulled it out of that equation and put it here. So this first one where we did this, we got the actual distributed capacitance of the line because that came from the inhomogeneous solution. Then from the homogeneous solution, we do the exact same line of code, but we use all the homogeneous solution terms, and we get the distributed capacitance of the air transmission line. This is not the distributed capacitance of the line, but what we can do is calculate the actual distributed inductance of the line. And we have a 1 here because we made it air everywhere around the line. So now we have distributed capacitance, distributed inductance. We can calculate the characteristic impedance of the line. If we want to visualize the fields, well, we've just calculated a composite column vector. We need to extract the EX and EY components separately. The X components is in the top half of that column vector, so it's just 1 to M, where M is the number of elements in the grid. And then the EY is on the bottom half. So we extract the numbers from the bottom half, and that's EY. Now we reshape our column vectors back to these 2D grids, and we have a V, an EX, and an EY, and now those are ready to plot. When I'm just playing around myself, I always use ImageSC because I can actually see what the data is. P-Color does some other things because it's made to do more of shaded images. If I'm doing something for a publication, I will go use P-Color, but ImageSC just works better for troubleshooting and looking at your numbers. And if I wanted to overlay vector arrows, I would use Quiver. And you can make some really neat plots if you plot the magnitude of the electric field with P-Color, and then you overlay that with the vector nature with Quiver. So you'd P-Color, draw the electric field, you would say hold on, then do the Quiver plot to draw the arrows, and then hold off, and you have a really fancy figure, in fact. Okay, some quick examples, and you can use these to benchmark your code. So we'll start off with an ordinary line. This is what we just modeled. And if you plotted your material arrays after you built them, they'd look something like this. Since this is isotropic, these off-diagonal terms are all zeros. And you'll notice the diagonal terms look very similar. And just depending where this interface lies, these two could be off by 1 cell in the vertical direction, but they're probably exactly the same. So we model it, and here's what the images look like. This is the scalar potential. This is the magnitude of the electric field. And here are the X and Y components of the electric field separate. And here's the grid parameters that I ended up using from that. And the impedance I calculate from this is 44.3 ohms. Next example. Now we'll give this an anisotropic superstrate and substrate. In fact, look here. The superstrate and substrate are the same tensor. So there's no longer air up here. We've essentially pulled the substrate up over the transmission line. And so the dielectric is really homogeneous. It's just anisotropic. So in fact, our 4 arrays are the same everywhere. We don't see any structure anywhere, but they're different values. And we'll see that it's a 3 in this array. This array has a 3.4 everywhere. This array has a 3.4641 everywhere, and this array has a 7.0 everywhere. But we actually rotated our tensor. We started with a tensor that had 1 and 9 in these two diagonal positions, and we want to rotate it to the left around the axis coming out of the plane of the board here by 30 degrees. So we calculate a rotation matrix. Remember how we did that in a previous lecture? So for negative 30-degree rotation, this is how we fill in the rotation matrix, and here's the numbers we get from it. Well, now we go down and we rotate our tensor, and after do a lot of work, this is what we end up with, and that was what I showed on the previous slide. So this tensor is really simply that tensor just rotated 30 degrees, and we ended up here. So when we do that, look what happens. The field is following that new direction. It's rotated to the left by 30 degrees, just as we would expect. And when we do that, the impedance is now almost 50 ohms. I want to end with one slide. The algorithm that we just developed does a whole lot more than just transmission lines. So we used it for that in this case, but what we have is something very generic. Given a distribution of metals forced to all kinds of different potentials, so here's some weird shaped metals all forced to different voltages, and then the question is, what does the potential look like between all of these blobs of metal? Well, what we've just programmed does that. And so here's what that potential might look like. So this is, you see we're forced to 7 volts, that's the dark red, and it grades down to 5 volts, grades down to ground, and we can visualize the potential around all these things. The algorithm we developed does that. We've added on to that, and from the potential we calculated the fields and calculated inductance and capacitance to eventually look at transmission lines, but this can do a lot more. We can calculate capacitance of a capacitor. I've used this in the past to look at the effect of shapes of nanoparticles and what shaped particles give a better electric response. This is something we'll talk about later in the semester, but there's all kinds of uses for this. And so the tool you have, having developed this, is a lot more generic than just transmission lines. You give it a bunch of forced potentials, and it calculates what the potential looks like all around that. But it can also do that in the presence of very strange and anisotropic dielectrics. So that's it for this lecture.